So we're going to switch to English because Bede is fun. So today we have Bede, who's going to present his work of his previous postdoc. He just started a new postdoc here with MARBEC and Ifremer under the supervision of Ffinian, Benoît and Nicolas Darrier, working on the osmosis model, coupling with another biogeochemical model. But today he's going to present us his previous work in Nantes. So go, it's yours.
Yeah, cool. Okay, thank you. So as Emmy said, I'm English, but so I'll be presenting in English. But if anyone has any questions in short French, I'll try and do my best. So I'm going to be presenting the work that I carried out over 3 years in Nantes, which was across a few different projects. So originally it started off as the Vicom project, but then moved into Rewrite and then a few other projects, which effectively was, the goal was to be able to map intertidal seagrasses across Europe, and sort of how we led to being able to create a full map of Europe of intertidal seagrass. But it's an initial map, it's not perfect, and there's still lots of work that is going on and will be going on to do with it. Lots of people were involved with the project, but this is the name list of everyone that was in the most recent paper. But like I say, lots and lots of different researchers have been involved. So first of all, kind of give a bit of background, proof of concept. So originally when we started the Vicom project, we were looking at using remote sensing, so satellite imagery or reflectance of the intertidal area. And we wanted to make sure that actually we could classify seagrasses in that area effectively and accurately. Then I'm going to go from sort of how we went from sampling in the field to drone, satellites, and different methods of mapping with satellites and drones. So going from the ground up. Then how we scaled up, looking at site-specific modeling and habitat classifications into more of a full European map, which uses a harmonized and consistent method across Europe so that we can sort of evaluate how accurate or uncertain we are. And then sort of once we scaled up to Europe, what are we planning to do next? What's sort of going on with the work now? So first of all, talking about intertidal habitats, they're a really integral link between the terrestrial and marine environments, but it experienced really extreme changes in their environment very regularly. So going from totally submerged in seawater to totally immersed and open to the air within a matter of hours, sometimes very fresh water, sometimes very saline waters. And a lot of the habitats that are there can form the baseline for a lot of important species, but also create structures. So you can see at the top photo here of Sabellaria reef, form really huge, especially in Brittany. There's some really, really big Sabellaria reefs, but also sort of oyster reefs. So there's just in the bottom of the bottom image, there's a bit of oyster reef next to the oyster tables. But the intertidal area is also really important for humans. So a lot of agriculture goes on in those areas, but also the areas themselves are used as nursery habitats for a lot of important and also quite often fishery species. And because of the cycling of nutrients between the terrestrial and the marine environment, it's really important for a lot of nutrient cycles, such as the carbon cycle, which is why seagrasses are now being talked about quite a lot because of sort of blue carbon discussions. So seagrass on the whole, not just intertidal seagrasses, are globally distributed apart from in Antarctica. This is quite an old map, so there are some gaps, but gives this general picture. Seagrasses on the whole, well, they're the only marine flowering plants that lives in the marine environment. And because of their importance within the carbon cycle and perhaps quite dominated by a lot of subtidal species that can sequester carbon, they've been named as a blue carbon habitat, similar to mangroves or salt marshes. But generally, intertidal seagrasses have been very overlooked. So quite often when you see even the last map I showed of a global distribution of seagrasses, there's no discussion of intertidal seagrasses, or they're grouped together with subtidals saying that they're very similar in their physiology or things like that, which doesn't really necessarily make much sense when they're experiencing very, very different environments. But because of their ecology, they're quite often in areas that are very high levels of anthropogenic activity. So they occur in estuaries or sheltered bays, places where humans really like to put ports and have leisure, boating activities and agriculture, like they said. So they're very close to anthropogenic activity, even though they're overlooked. So why is that? So I have after a few years of working in the intertidal area, I have a few thoughts on why that is. First of all, it's quite difficult to sample in the intertidal area. Physically, it's really draining to try and cover even a few meters of the intertidal area where seagrasses are. And actually can, because of time restraints in the intertidal area being exposed, it can be quite a short period of time that you're actually there. So you need to get there, you need to get your samples, get out. Which, if you lose, for example, this is me holding my last wetsuit boot on a sampling trip because I lost the other one. It can become quite expensive if you lose equipment or you have to abandon your equipment to get away from the upcoming tide. But also, it's a huge area. So going across that area and being able to sample it fully is really difficult. It's going to take a lot of money, a lot of resources, and just fairly unfeasible to cover the whole area. So the idea behind this work was we were going to use remote sensing. So looking at the reflectance with some sort of sensor to be able to map the area, because we can cover a lot bigger area with remote sensing. So what is remote sensing? So really generally, we rely on the fact with remote sensing that the sun sends down basically every wavelength of light that you can think of, and non-visible wavelengths of EM spectra. And then when it hits a target, such as seagrass, it then reflects a certain wavelength back, but some of it's absorbed, some of it's not. So we can take advantage of that by having some sort of sensor that can pick up that change in wavelength and try and classify our environment. And there's multiple different levels of remote sensing. So you can do it with a sort of handheld device. This is me, I think it's in Brittany, with what's called an ASD. So it's a hyperspectral imager. It can take really fine scale spectral resolution data. Or you might have a drone that has some sort of camera on it, or LiDAR, or any other sensor, and then also satellites. So the idea of our work is to go from our samples in the field that are really close, really high resolution spatially, and really high resolution spectrally, and then try and scale that up to the satellites that are, well, we will be using an ocean access one, but there's lots and lots of different satellites you could be using. But generally, there are quite a lot of trade-offs between what resolutions you have and what scales you have. So satellites are covering really vast areas, but generally a pixel size is, well, the really expensive satellites you can get maybe 30 centimeters, 1 meter, but a lot of them can be hundreds of meters, maybe even kilometers, depending on what you're looking at. And some satellites come back every day, some are every month, some are once a year or once when you ask for it. And so we were quite interested, first of all, at looking at the multispectral, the spectral idea, that quite often satellites that are open access and have lots and lots of data free accessible are multispectral sensors. But that comes into question how we can classify the seagrasses. Thankfully, in the intertidal area, at the Sentinel-2 or the satellite pixel size, there's quite a low diversity of vegetation. So anything that we might be confusing with seagrass, there's only a few options that you could have that actually would be covering similar sort of areas. There's obviously a lot of diversity within those and any fauna within them, but generally speaking, at satellite scale, at habitat level, there's not many. So when we've got this low diversity, but also low spectral resolution, can we detect it or can we distinguish it with remote sensing? So that was the first sort of project that we went through, was using our hyperspectral data. So we collected a library of hyperspectral samples across the classes that we wanted to see, or we would see in the intertidal area, which include, so the diatoms at the top, Manuel is the name we'll have the seagrass, Phaeophysi for generally brown algae, Olophysi for the green algae, and then Xanthophysi, which is, it's a yellow-green algae, but actually not that common. But anyway, So we could take these spectral data and say, if we were looking at them, how similar are they across our classes? And actually, the main problem that we might have with seagrass is its confusion with ulvophytes, so the green algae. But as you can see from the hyperspectral data, they don't fully overlap. There's differences. They have very similar pigment compositions, but for example, in the near infrared, so from about 700 nanometers onwards, they do have a different near infrared plateau. That means that we could potentially use this information for distinguishing at hyperspectral resolution. But what happens when we degrade the signal to that of, say, Sentinel-2 at 20-meter resolution? And we see that we get a lot less information from these degraded spectra. They're a lot more similar to each other, especially the Maniloxter and the Ulvophytes, so the green algae and the seagrass. But still, there are differences. So we trained a few models and looked at how effective and accurate would we be at classifying these different intertidal vegetation classes with different resolutions of spectral information. So we took 5 different sensors that are widely or openly available for satellites and saw how accurate we would be if we were using that spectral resolution. So on the x-axis, we've got the spectral resolution, and it's very discrete because we wanted to look at actual sensors that are available. But you can see that generally, once you get to about 10 spectral bands, which is around the Sentinel-2 resolution, when it's at 10 meters or 60 meters, and also our drone, which is right next to it, when we have that sort of spectral resolution, we found that we can be quite accurate, and actually increasing the spectral resolution didn't necessarily improve our accuracy at identifying the intertidal vegetation. It might be very useful for different tasks, but for this specific task, it didn't actually improve our accuracy or our sensitivity of the model. So from a spectral point of view, we're able to distinguish seagrass from the other intertidal classes. But how do we go from that spectral, that in situ sample of reflectance, and then go to the satellite level? We need some sort of step in between to create a large training data for some sort of model for Sentinel-2. Therefore, we use drones. Good intermediary step. And so we flew drones across different parts of the Atlantic coastline of Europe, from sort of Brittany coastline down into Portugal. And basically, because of the pixel size, so we had, depending on how high we fly with our drone, we would have 8mm or 80mm pixel between those two sort of values, pixel size, which means when you look at the image, you can identify it. You can see, you can say that's seagrass, that's green algae, that's brown algae. You can do visual classification, which makes it a really useful tool for being able to identify a huge area. So this is actually work by Simon Warrier, who's the researcher who's a drone expert, great guy. We developed a model that was actually using the drone data to be able to classify our habitats. And I think it's 96% accurate across our classes and across our our different sites. So we could use that as our training data for Sentinel-2. So this is our sort of ground-up methodology where we start in situ, then we have drones, and then the drones can create a huge labeled data set for Sentinel-2. So at that point, we created a new model because we just love creating models. And I love creating acronyms. So this model is called ICECREAMS, which is the intertidal classification of Europe, categorizing reflectance of emerged areas of marine vegetation with Sentinel-2. A lot of these projects are funded by the European Space Agency, which is based just outside of Rome. So we were in Rome having lots of ice cream when I thought of this acronym. So there was something there. So this classification is, this model is a neural network classifier that we validated with totally independent data, about 60,000 pixels worth of data, and we got 92% accuracy at classifying seagrass. And then we applied this model to multiple sites across Europe. And when we've got our area that is classified as seagrass, which is this sort of dark green area here, we can then convert that into some sort of cover based off of the spectra that are in those pixels that can give us some sort of distribution of seagrass cover. So then we applied it to multiple sites across Europe. So we found sites where we knew there was seagrass, and we knew other researchers had done work in those sites, and we created time series. And one of the interesting things, like I say, quite often intertidal seagrasses have been lumped together with subtidal seagrasses. But when they hadn't, when intertidal seagrasses had been looked at and looked at their sort of temporal changes, there was this idea of phenology where the above ground biomass totally dies off for a large portion of the year. But in Europe, that was, in a lot of the literature we were reading, was assumed or implied to be consistent across Europe. So that timing of when the peak and when the maxima and the minima, so the peak and the trough of biomass or leaf biomass, it was assumed to be fairly consistent across Europe, which we showed was just not true. By looking at these different sites, and you can see that as you go left to right, top to bottom, you go further south, we're finding very different phenologies of intertidal seagrass across Europe. So starting in the sort of north or the top row, really, you have quite a clear maximum and minima. The maximum is happening from end of summer to sort of autumn time in the northern hemisphere. And then during winter or the sort of the minima, the seagrass is going to almost nothing. There's almost no biomass, there's no leaves that the satellite is able to detect. But when you go further south, you actually find that it very rarely goes to zero. We're seeing a much more dampened phenology. There's far less extreme between the minima and maxima, but also that the maxima and minima are becoming later in the year. And if you look at it versus latitude, you see it's quite a consistent linear pattern of the further south in Europe you go, the further later into the year the maxima and minima become. So once we had so we did a few papers looking at these sort of time series within sites. We realized that actually, if we wanted to be able to create a map of Europe, we would need to have some sort of consistent method or methodology that would allow us to apply this model across the full intertidal area of Europe, but in a consistent way so that the imagery, for example, is low tide, there's no clouds, it's only the intertidal area, we're not looking at terrestrial, we're not looking at subtidal anything. And so we developed a workflow, which is horrendously complex, and I will go through it step by step, don't worry. So the idea is basically we needed to have some sort of image of Europe when those pixels in the intertidal area were low tide. But first of all, there we go. So first of all, we basically wanted to mask the intertidal area. We wanted to select the area that we were looking at and only select imagery from within the intertidal area as it's defined by an open access map by Murray 2019, which is an open access data set that shows you where the intertidal area is from that paper. But we also, like to say, we wanted to make sure that we didn't have any clouds in our imagery. And there is a whole very complex method for detecting cloud within imagery that Mara Rocamora sort of helped me with and developed in her paper. That meant we could filter down this stack of imagery so that we've only got intertidal, low tide, and cloud-free imagery. From that, we can then create what's called a composite or a quality mosaic, where we take for every single pixel that we do have imagery, we select the time when that pixel was the most vegetative. We use something called the Normalized Difference Vegetation Index, NDVI, to select the times when the pixels were at its most vegetation, second most, third most, fourth most, and fifth most. So we create 5 composite images of the intertidal area of Europe when it's at its most vegetative. It's a horrible word to say. And then once we've got that, we can apply our ice cream model to it. So creating the top 5 vegetation maps of Europe that have all our different classes. and tell us when these areas were seagrass, when these areas were something. And so to be cautious, so we're not perhaps increasing our uncertainty, to say that somewhere is seagrass or a pixel in our European-wide map is seagrass, we decided we wanted to take the mode class across those 5 images. So it has to have at least 3 pixels or 3 times where that pixel was classified as seagrass for us to say that it is seagrass. If it has 5, we're more confident of it being seagrass. And if it has less confident. And that allowed us to create our map of Europe. Yeah, and that's the whole workflow. And it's consistent. We've applied this across the whole of Europe and have created quite a nice little app that means you can inspect that data. So it's a little bit laggy because it's a bit slow, but it's we created this map, the initial map of intertidal seagrass in Europe, and have created this app, which you can go to this link. It's all open access. You can access it, which not only shows you the seagrass cover, but it also shows the uncertainty we have of that seagrass cover, which again is based off of how many times across our 5 composites we found it to be seagrass based off of our model, but also using our model accuracy itself. But also when does it happen? So what time of the year is the seagrass at that point at its maximum, and in which year? So there's multiple years of data, so we also put in the year. And so we can summarize these data in lots of different ways. First of all, we looked at where there might be hotspots. So seeing where are there areas that have a lot of seagrass versus less seagrass. And found that actually you can find quite large hotspots of seagrass or intertidal seagrass across the range of Europe. So starting off in the North Frisian Wadden Sea, there's huge intertidal areas there. And there is a lot of intertidal seagrass. And likewise, so you go into France, you've got Bordeaux Bay is quite a big one, but Arcachon Bay is a really massive intertidal seagrass bay, although in recent years it's becoming less, apparently. And then down to sort of Portugal and Spain, Rio Formosa in the south of Portugal also has a very big seagrass bed. And then we wanted to sort of test our theory of phenology, and we could do this a bit more continuously rather than having individual points. We can now see that actually, yes, our stipulation that we think there's a fairly linear trend, almost linear trend of timing of seagrass peak is with latitude. Well, as you go further south, it becomes later. So that was a nice sort of coming at the same answer from 2 different ways, which I quite liked. But we also saw other latitudinal patterns. So from the north to the south in Europe, we find that actually more of the intertidal area is covered by seagrass. Not a huge amount, but still only getting to about 5% of the intertidal area when you're further south. But it is becoming more seagrass dominated in the intertidal areas. But not only that, we could also find that the seagrass that is in the north is far more likely to be lower density. So when we've got sort of the seagrass bed, for example, in the North Frisian Wadden Sea, that's a huge area, but a lot of it's around 50 or 60% seagrass cover. It's not really high density seagrass. Whereas when you go down to Rio Formosa, it's a much smaller area, but it's really dense, 100% cover, almost all of the area there. It's really high density seagrass, which is quite an interesting result. And that comes from our most recent paper. And once we had this data, we've made it open access, and the papers are all open access for all of the steps of this. We're sort of now thinking, why would we stop at Europe? The data are from Europe that train the model, but actually, I've now sort of applied it across Europe. We've been in contact with lots of researchers from different places. Sorry, not Europe, around the world. South Africa. So we've applied it in different places. We've contacted researchers that do intertidal seagrass work in these areas. And so far, we're still sort of working out a few of the kinks and making sure that we're being accurate. But across, well, we've got training data from Mauritania, we've got some from South Africa, we've got some from Quebec, we've got data from Australia. There's quite a lot of open access data through Seagrass Spotter. we're getting quite good accuracy. I think we've got 205,000 pixels of validation, so labeled data globally, and our model's coming up at about 84-85% accurate. This is still ongoing, but is what I think is quite a cool thing that we could have a full map of Europe, full map of the world, sorry, for seagrass or intertidal seagrass. We'll do for that one. And the ideas I'm sort of looking into are actually not just having a map, but also seeing, so intertidal seagrass is, like I say, quite overlooked generally, not just in Europe, but globally. And whether certain areas of intertidal seagrass, certain countries, certain regions have more protection that sort of aligns with where the seagrass is, but also would that protection actually be effective? Even if it's not directed at protecting the intertidal seagrass, would it actually influence the intertidal seagrass? Would it be protecting it? And so that's sort of next steps that I'm wanting to go into. Right. All right. So summary, we've created an initial map using a consistent and harmonized methodology. All of the data and the methodologies are all open access and following what the FAIR principles, findable, I can't remember the acronym now, accessible, interpretable, repeatable. So we've tried to follow that throughout. So all of the papers have been open access. The interactive map is totally open access. You can go on the link and find it. There's also a Zenodo archive with the actual TIFF, the raw data itself that's used to create the map. And we've mapped quite a large area, so 15,000 kilometers squared, the intertidal area. Not found a huge amount of cumulative seagrass, so only 212 kilometers squared. But it's also, there's quite a lot of area there. 20 kilometers squared is a huge area. How is your plus minus? It's about 10% error in that thing. We know the map's not perfect, but we think it's quite a good starting point. And hopefully people can use the code for their own location or perhaps do other studies around it. So like with all of these sort of projects, loads of people that have been really, really helpful. I want to give a really special thanks to Laurent Barrier, Pierre Genès, Simon Murray, Lara Zoffoli, Maroka, Filippo Rosa, and Vona Meledor for making my time in not really great, but also being able to smile when it's torrential rain and you're meant to be going into the field and you let the old people go into the field while we're still on the bank. But also, helping out with sort of any sort of scientific queries and being really, really, great people. So thank you all for this.
And also online.
Is there any question online? Maybe first.
I can start. I had one question on especially on the phenology and the fact that there is latitudinal change, but I was wondering whether data exists on Sentinel, for instance, on the past, so that you could also look at how technology changed over time.
Yeah, so this is one of the big things with using Sentinel-2 data. It starts in 2017, 2016, really, if you want it to be usable. There are obviously, if you go to Landsat or some of the other open access satellites, you can go back to the 80s with that. The problem with that is with Sentinel-2, you've got 10-meter resolution. With Landsat going back, you've got 30, maybe 60-meter resolution, which, especially for some of the smaller seagrass beds, it would just wipe out most of the heterogeneity in distribution that you're seeing. I mean, even the 10-meter resolution of Sentinel-2 is missing below pixel variation that's going on. So potentially, yes, we could do that. But one of the things, we would then have to create another model to be able to do it. And that's where...
That's why we didn't go for it.
Yeah, we didn't go too much back into the past for that. Mostly because it would have been a whole other project of a similar size. Create the model, have all the training data, validate it, do that, and then look back into the past. But
But then with this model, on the future, it would be global.
Yeah, so this is the thing, the model itself, well, I didn't sort of mention it, but for the worldwide stuff, I did a slightly different compositing method, using more up-to-date data, but less, in fact, in 3 years rather than 5 years, which probably has its problems and has its advantages. But yeah, so it should work into the future. One of the things as well I haven't really mentioned, but especially when we're doing our proof of concept work, we looked at sort of which spectral regions across different satellites were really important. And one of the things we highlighted was there's a few different regions, but I think it's about 740 nanometers is really important for vegetation detection, at least with the intertidal vegetation, but I'm pretty sure it's the same for a lot of other vegetation classes. And that's missing from almost all satellites that are currently available that aren't hyperspectral. And based off of that work and a few meetings, there is now a band exactly where we want it to be in the plan for Sentinel-2 next generation, which will be coming in 2030. So yeah, so that was quite cool. I think it's a combination of lots of people asking for that band, but yeah, we specifically said in our paper, and then 2 months later they said, this is what we're planning to do. So that was fine. Yes.
You look at the timing of the peak of seagrass coverage, etc. Did you look at the links with environmental viable peak like temperature or nutrient cycles?
Yeah, absolutely. So yeah, that was one of the things in the paper that's in communications environment. This one. Yeah, we did exactly that. So we looked at temperature. We sort of, yeah, that was one of the reviewer comments, was to add in the environmental thing. But actually, from my point of view, we were more just looking at what the timing of the seagrass is. And I think it's a dangerous path to say 1 or 2 or even 3 environmental variables are the things that's driving it. I think it's probably a massive combination of lots of different things that are all interrelated. So yeah, but no, we did do that. That's in the paper, and we found that yeah, temperature aligns quite well. I think we did temperature. What does PAR stand for? I can't remember. Photosynthetic radiation. Can't remember. But yeah, basically the amount of sunlight we also looked at for seeing that, and that seems to be yeah, it's pretty consistent. I guess a latitude, not gradient, but not.
And for example, with marine heat wave or like the impact of such extreme events?
Really pleased you asked that question. This week, there's another paper published by Simon that we did exactly that. We looked into sort of marine heat waves. We didn't do it in stuff I've looked at here, but actually Simon did some laboratory experiments. So we took seagrass into intertidal chambers. We looked at the response of seagrass reflectance to heat wave events, published in Remote Sensing Environment. It's a really cool paper. Definitely go and check it out. But yeah, so we did look at the marine heat waves, and actually for well, it was marine and environmental heat waves, because obviously half the time it's environment, half the time it's marine. And we found that actually the main issue for the seagrass was the environmental heat waves. So the air temperature was a lot more of a factor in sort of preliminary analysis. So we kept to that rather than having to have sort of combined effects versus separate effects and things like that. Because again, the seagrass themselves, when you've got a marine heat wave, it's going up by a few degrees temperature, but actually the seagrass itself, the tidal cycle will be experiencing much wider variation in temperature. So we looked at more the environmental side. But yeah, it's really cool. There's a whole thing to do with the leaves go really dark, but they're still there, and you've still got quite a high NDVI, so you can still detect them as seagrass. And we've done it in a few things where we could find that they were still seagrass, but they were a totally different color. They were no longer green, they were brown. Yeah, and small but really cool index for being able to detect that change.
You can answer my question. You said that it's used for conservation matters, for example. Do you expect people to use it for other things? You have an idea that you use it for developing?
So there's a few things that came out of it. So we looked at quite a lot of, so I said we used the Murray et al. Intertidal mass thing. And we found it was, in some places it was working really, really well. Globally, it's 82% accurate, but 20% of the globe is quite a large area to be getting wrong. And so there was a few things that we sort of developed to try and improve that, which has obviously, has sort of influence on coastline changes and things like that, which has implications on erosion, whether coastal erosion is going on, how fast, those sorts of things. And that was what Maria was doing that paper for. With the seagrass itself, I know there's a few different places, for example, in Jersey, in the Channel Islands, where a lot of anchorages are on places that are intertidal seagrass beds. And it's fairly well protected there, but I think in certain areas in the world it's not. So it could be really influential for that. It's more of a conservation thing still. But yeah, there are probably multiple uses, mostly ecology and conservation based, though. I can't think of any. If you can think of any, tell me that.
Do you think using your map you could calculate the contribution of intertidal seagrasses to carbon cycle?
I really don't want to do that. No. Yeah, it's a really good question, and actually, that's one of the things we've been discussing. There's a fairly recent report by the UK government that shows that intertidal seagrasses have a similar amount of carbon as totally bare sediments. So I think so a lot of the stuff to do with sequestering carbon, especially because the biomass is disappearing every 6 months. You have no leaf biomass, which is what's meant to sort of allow that sequestration. So I think when you're talking about sequestration with seagrasses, it's more of the subtidal species such as Posidonia is the big one. But there's some studies with Saucer marina as well. Yeah, I'm hesitant to go down that route. I think it's a slippery slope. You could extrapolate it and say this is the amount of carbon in tidal seagrasses, but I think it would change every 6 months, and then it's not sequestration, it's just carbon stuff, and that's the whole thing. But yeah.
But given what you said, it means if you go to the south, you have an increase of carbon sequestration because the minimum is not zero.
Perhaps I haven't looked at it, but there's always seagrass leaves are always there throughout the year. It's a lower density and a higher density, but there's also some sort of physiology going on where they do discard their leaves continuously and regrow continuously. So it's not the same leaves throughout the season.
Okay.
And yeah, there's also some problems of epiphytes growing on the seagrass leaves at that point as well. So, but no, so there is potential that actually sort of in the sort of further equatorial regions would have more sequestration in intertidal seagrasses. But the rewrite project, which I'm quoting, we've done quite a lot of coring in seagrass beds, which is where I lost my wetsuit boots, looking at carbon storage, and that is ongoing. So yeah, and that is down in Cadiz, so in the south of Europe. So it's one of the places that it could have seagrass. They're also doing it in France, in Port Bay, and I think it's somewhere in the Wadden Sea. So yeah, that is ongoing. Yeah. Yeah.
You work on the native seagrass.
Sorry?
You work on the native seagrass.
Yeah, there's no real intertidal area. So yeah, almost all the seagrass in the Mediterranean is subtidal, or when I'm saying intertidal, I'm also specifically talking about areas that are totally devoid of water at low tide and totally covered at high tide. So that removes habitats like salt marsh and mangroves, which, while the roots are getting covered by water, and then the biggest tides, they will be covering salt marshes. The vast majority of the time, those are out of the water. And so we didn't consider that. But yeah, it is in the map, the Mediterranean area, but there's almost nothing predicted. It's like 2 or 3 orders of magnitude smaller in area, so we didn't actually assess it for the paper. But it is in the supplementary materials.
Is there any question online? No. Well, thank you, Bede. Thank you, everyone online.
You guys. Bonne journée, à bientôt.
À bientôt. Au revoir.
À bientôt.
Merci.